Good evening, everyone. Good evening. Am I audible?
Yes, sir.
Yeah. My screen is visible to you guys.
Yes, sir.
Okay. So हम लोग रॉकेबल कंप्लीट कर लिए थे. So moving on to the next topic. Any confusion in rockable pyrolysis? Any confusion? Any doubts?
No, sir.
Okay. So write down the next topic. Time temperature index. Okay. My like that whatever I am writing is visible to you. Or like it is somewhat blurry or something. Is it clearly visible?
Yes, sir.
Because yeah, because I am using a new device. Okay. So so this is also a method to determine the petroleum potential. Okay. So what so write down few points in time temperature index. So as we know, like maturity is affected by two things. First is time and second is temperature. So using these two factors of maturity, someone designed the time temperature index. Okay, maturity is determined by time and temperature, and that's why we are like employing time temperature index. So write down the first point. Oil generation is promoted at high surface temperature. Okay, this means that like if the temperature is high, then the chances of the oil formation will be also high. Okay, so as we already discussed that maturity depends on both on time and temperature. So write down this point. Rate of chemical reaction depends upon the temperature. You guys must have studied this in the chapter chemical kinetics in chapter 2. Sorry, in class 12. Like the rate of chemical reaction depends on temperature, and the relationship can be given as K is equal to A into E to the power EA divided by RT. This whole thing, that is EA by RT, is in the power of E, where K is what? K is the rate constant. That is the rate at which the reaction is taking place. A is Arrhenius constant. Okay, and your EA is activation energy, and R is universal gas constant. You guys know the value of R na? The value of R is 8.314 joule Kelvin inverse mole inverse. So if we are writing in the if we are writing expressing R, that is universal gas constant, in the form of joule employing energy, then we will write joule Kelvin inverse mole inverse. The other form to write this is R is equal to 0.0821 liter L for liter ATM Kelvin inverse mole inverse. Okay, liter is for volume, ATM is for pressure, Kelvin is for temperature, and mole is for number of atoms. Okay, so this formula gives the rate constant of a chemical reaction. So write down the next point. Rate of chemical reaction becomes approximately double. Okay, approximately double when the temperature is increased by about 10 degrees Celsius or say 18 degree Fahrenheit. So this point, like the if we increase the temperature by 10 degrees Celsius or 18 degree Fahrenheit, then the rate of chemical reaction, that is K. Okay, K becomes double, and this double value comes from this equation. Like if you solve this two equation, K is equal to A to the power minus EA by RT. This is the value of K1, and this is the value of K2 at if this K1 is calculated at temperature T, and this K2 is calculated at temperature T plus 10 degrees Celsius or say 18 degree Fahrenheit, then we will get A to the power R, and this T we have added 10 degrees Celsius now, therefore we will write T plus 10 degrees Celsius. But like for example, if we are using the value of R is equal to 0.0821, then we have Kelvin inverse. Therefore, we will have to write the temperature here in Kelvin. Okay, so that like the unit of a single quantity remains same everywhere in the equation. Like we cannot use for a single quantity, we cannot use two different units in the same equation. We cannot use degree Celsius and temperature is equal to degree Kelvin in the same equation. So you guys must remember this while solving any numericals. Like for a single quantity, the unit of that quantity should remain same in a particular equation. So if we are using this value, then we will use temperature in Kelvin here. So if we compare this K1 and K2, then what we will get that K2 is approximately two times of K1, and that's what it is said in the previous equation, that the rate of chemical reaction becomes double. Okay, so this equation is also valid for hydrocarbon generation also, and hence write down amount of hydrocarbon generated increases linearly with time and increases exponentially with absolute temperature. Okay, done.
It increases linearly.
What you said, like your voice breakdown. Can you repeat?
Increases linearly. Then what is written?
Amount of hydrocarbon generated increases linearly with time and increases exponentially with absolute temperature. Okay, like amount of hydrocarbon will be directly proportional to time and or exponentially proportional to temperature. Exponentially. Okay. Then so write down the next point in time temperature index. So as we already know, both time and temperature are important processes are important processes in oil generation and in subsequent cracking of oil to gas. We know now, like if this is the organic matter, then it will convert into oil, and then oil will be converted into gas, and that's what it is said here. Like with increasing time and temperature, the organic matter will convert into oil, and then oil will convert into gas. Then, so like in the equation, K is equal to A into the e power EA by RT. That is this equation. This red one, we have used a term activation energy. So what is the concept of activation energy? So activation energy means the energy required to initiate the reaction or initiate the chemical or say the chemical reaction. For example, like if this is a piece of wood, okay, if this is a piece of wood and you like if you try to burn it with a matchstick, if you try to burn it with a matchstick, like this thick wood, like the wood is very much thick, okay, and you are trying to burn it with this matchstick, so you will not be able to do that because the energy provided by the matchstick is not being able to initiate the burning process. So a certain amount of energy is required for burning that thick wood, okay, and that energy is called as activation energy. Okay. So to start a particular reaction, you need a certain amount of energy. If your energy is below that, the reaction will not start. For example, if we heat the wood with a large fire, then the wood will start to burn. After the wood has started to burn, then the amount of energy required to keep this wood burning will be less. सो व्हाट आई मीन टू से इज अगर एक बार इस मोटे लकड़ी को जला दिया गया, जलाने में बहुत ज्यादा एनर्जी खर्च होगा कि लाइक बहुत अमाउंट ऑफ एनर्जी लगा तब जलना स्टार्ट हुआ, लेकिन इसको जलते रखने के लिए बहुत कम एनर्जी लगेगा, मतलब थोड़ा सा भी अगर हम आग इधर से देते रहें तो ये लकड़ी जलते रहेगा. इट मीन्स लाइक स्टार्ट करने में ज्यादा एनर्जी लग रहा है एज कंपेयर टू कीप ऑन द प्रोसेस. So that's what we will be seeing here. So write
Sir,
down the value of EA. Yeah, hi.
sir, your screen is getting blurry sometimes because probably this is for red pen. Can you please change it or
Yeah, yeah, okay.
reconnect it?
Yeah, do let me know. Okay, I have changed the color of the pen. EA. So what I said is like to start the reaction we need a large amount of energy, but to keep on the reaction going we need a lesser amount of energy. Okay. So EA is the activation energy. So EA is around 11,000 to 14,000 calorie per mole. Calorie is the unit of energy. So this amount of energy is required for oil generation. So this energy can vary from 11,000 to 14,000 depending on different basins. So this amount of energy is required for oil generation. So this is very low. Okay, very low amount of energy. Is the screen blurry now?
Yes, sir.
Yes.
Yes, sir.
Okay, I'm trying to reconnect then. The writing is not clear. The screen is hazy. Okay. Is it good now? Hello?
No such screen blurry. You can continue with the black pen, please, because the red pen is getting more blurry. So please continue with black pen.
Yeah, I'm using black pen.
Yeah, yes.
So this thing, like you guys can read it, like whoever is speaking now, can you please read out the sentence where I am circling?
Yes, amount of hydrocarbon generated prevails. Something is not getting clear. Uh,
Increases,
with that, increases. That part is not clear for me.
in,
I don't know for
increases,
others.
increases linearly with time and increases exponentially with absolute temperature.
As you speaking and writing, that's is for easy for everyone, I think, because every time that writing is not clear, so I don't
Okay.
know what for others.
So Whatever I am writing now, is this
Yes,
is clear?
that's more clear. Yes, 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 yes. You can continue with it.
Okay, okay, thanks. Okay, so we studied the concept of activation energy. So activation energy is the energy required to start a particular reaction. So what we discussed here, like if you try to burn a wood with a matchstick, it is difficult. So the amount of energy required to burn a thick log of wood is large, but to continue burning that wood, a lesser amount of energy is required. This means that energy energy required to start a reaction is greater than energy required to continue that reaction. This is clear now?
Yes, sir, that's
Okay. So we were discussing the amount of activation energy required for oil generation. So the amount of activation energy for oil generation is 11,000 to 14,000 calorie per mole. Okay, this amount of energy is required for oil generation, and this is low. Okay, and write down, and EA is about 40,000 to 60,000 calorie per mole. This amount of energy is required for breaking of CC bonds of organic matter. So like when the organic matter is being converted into kerosene. Okay, during this process a lot of carbon bond breaks. So during the initial phase of conversion of organic matter to kerosene, like this is the process now, organic matter is converted to kerosene, and then kerosene is converted to oil, and then oil is converted into gas, and then we get graphite, or say nascent carbon in the ultimate stage. So during this phase, organic matter to kerosene, the amount of energy required is large. That is about 40,000 to
Sir, what is
60,000.
written? CC bond.
Yeah, CC, carbon bond. In this stage, from organic matter to kerosene, the amount of energy required is 40,000 to 60,000. But from kerosene to oil, the amount of energy required is around 11,000 to 14,000. So this was the concept of activation energy. During the initial phase of conversion, a large amount of energy is required, but during the main phase of conversion of kerosene to oil, a lesser amount of energy is required. Clear?
Sir, what is written that organic matter after that?
Das, like this is an arrow.
या नहीं, वो ऑर्गेनिक मैटर के एरो से नीचे जो लिखा है ना।
Yeah, I wrote like organic matter is converted to kerosene. That's why I gave a arrow here and wrote kerosene. Okay, and then this figure, this chart, organic matter to kerosene, kerosene to oil, and then oil to gas. Done. So under the same time temperature index, write down theory of Lopatins method. This theory is also based on the concept of time and temperature. So this theory also says that both time and temperature are important for oil generation and in subsequent cracking of oil to gas. That's what why we discussed in like the TTI, time temperature index. And this method also says that both time and temperature, firstly write down both time and temperature are important, IMP are important processes. Like this is a physical quantity, time and temperature, but I am writing processes. It was like time and temperature act for a long time and they act as a process. Both time and temperature are important processes in oil generation. Like this is a common point. And then the next important point is both this these two factors are interchangeable. Okay, interchangeable means if you are providing large time, then you will need a lesser temperature, and if you are providing less time, then you will need larger temperature. That's what we discussed now. Like if we if we are if we are finding oil in a Mesozoic basin, okay, so oil can occur in shallow depths also, because like for Mesozoic basin, time is large. Okay, time is large, and shallow depths means temperature is low. So for Mesozoic basins, we can find oil at shallow depths also, because time is very large and time is a large amount of time coupled with even a lesser temperature will be able to produce oil. But for Cenozoic basins, okay, for Cenozoic basins, time is less. It is less older, no, less older. So we will find oil in large depths. Large depths means large temperature. Okay. So what you can write down here is high temperature. Okay, I will write down in the next page. Like this thing is done now. I'm changing the page. Okay, done. So explaining the above concept, high temperature acting for short period of time can have the same maturation effect as low temperature acting over a large or say long acting over a long period of time. So either you keep the temperature high or you keep the time high. High temperature, high temperature can be coupled with low time. Okay, or say low temperature coupled with high time. I have written down a equal to mark here. The equal to mark means same maturity, same maturity effect. So these two factors can be interchange. Then any confusions in this? Any question?
Sir, last point is not clear. Same maturity effect.
Like I said, na, like if for a Mesozoic basin, time is large. So even if the temperature is low, the oil can mature. But for Cenozoic basin, time is time is what? Time is less because Cenozoic is like recent. That's why a large temperature is required for generating oil. Okay. Maturity depends on what? Maturity depends on time and temperature. Okay. So either you keep the time large or either you keep the temperature large. Okay. If you keep time low, if you keep time low, then you must keep high temperature. You must keep high temperature so that the oil can mature. Otherwise, like if you have high temperature, then the oil can mature in low time also. You can interchangeably say that. Okay. If you keep the time high, then the oil can mature in less time. If if you keep the temperature high, like if you keep the temperature high, then that oil can mature in less time. If you keep the temperature low, if you keep the temperature low, then the oil will take large time to mature. Now it is clear.
Yes, sir.
Okay. Okay, done. Moving on to the Lopatin's factors. So write down Lopatin defined two factors. Okay, TWO2 factors. First is an index value, and for temperature. For temperature intervals of 10 degrees Celsius. Then the zero value of n was arbitrarily. So whatever we are writing is to define a formula for time temperature index, or say the Lopatin's method. And for that, Lopatin defined two factors. First is n. Okay, and n is an index value, and it depends on the temperature intervals of 10 degrees Celsius. The zero value of n was arbitrarily chosen for the interval between 100 degrees Celsius and 110 degrees Celsius. Okay, so this range, zero was chosen. Zero was chosen for this range. So if the temperature is 100 degrees Celsius, okay, if that if the temperature is between 100 degrees Celsius and 110 degrees Celsius, then the value of n will be zero. If the temperature becomes if the temperature becomes between 90 degree to 100 degrees Celsius, the temperature has decreased. See, from 100 we have moved to 90 to 100. So the value of n will be minus 1. So n is defined. N is defined for this range, and is chosen 0 for this range. For 100 and for the temperature between 100 degrees Celsius and 110 degrees Celsius, the value of n will be 0, and n will change in intervals of 10 degrees Celsius. So we have decreased the temperature by 10 degrees Celsius here, that is 90 to 100. So the value of n will be -1. If we increase the temperature by 10 degrees Celsius, so our range will be what? 110 to 120 degrees Celsius. So for this, the value of n will be +1. Clear? Similarly, for 120 degrees Celsius to 130 degrees Celsius, value of n will be +2, because like we are 20 degree above this range. 110 na, one, like, see what was our range for 0? Sorry, yeah, this is our range for n is equal to 0. So add temperature 20 degrees Celsius both side. So what we will get? 120 degrees Celsius to 130 degrees Celsius. So value of this will be n is equal to 2, because we have increased the temperature by 20 degrees Celsius and changes in the interval of 10 degrees Celsius. If the value of temperature increases by 10 degrees Celsius, then n will increase by 1. Okay, so we have increased the temperature by 20 degrees Celsius. So the value of change, so the value of n will be changed by 2. Done. Write down this. This part is done. Anybody respond? Hello.
Yes, sir.
Okay. So the next factor of Lopatins, factor B. So this factor is a temperature factor. The first was an index value, a temperature factor, represented by gamma, equal to R, where R is the factor by which rate of maturation increases for each 10 degrees Celsius rise in temperature. 10 degrees Celsius rise in temperature. So what we are trying to do is we are trying to quantify the maturation. So okay, that's why like this temperature factor is an attempt to quantify the maturation process. Okay, so the formula is gamma is equal to R to the power -3 for the temperature interval of 70 degrees Celsius to 80 degrees Celsius, and gamma is equal to R to the power 3 for the interval 130 degrees Celsius to 140 degrees Celsius.
Hello, sir.
Yeah, hi.
Sir, the first one is r to the power -2 or -3.
For the first one, gamma is equal to R to the power -2, and for the second one, gamma is equal to R to the power 3. Done?
Okay, sir.
No, this one is also 3. Correct it down. This one is also 3, minus 3, and the next one is plus 3. Okay. So like we studied in the Arrhenius equation. Arrhenius equation says that quantifies the rate, na? K is equal to A into e to the power minus EA by RT. And we studied that like if we increase the temperature by 10 degrees Celsius, then the rate of the reaction becomes double. Oh, we compared, na? We calculated K1 and K2 for a increase in temperature of 10 degrees Celsius. Then we found that K2 is double of K1. That's therefore we can say that like this R is what? This R is the rate of maturation. So we can take this as the rate of reaction, and hence R can also be taken as 2. Okay. So write down R can be taken as 2. R can be taken as 2 according to Arrhenius equation. Arrhenius equation in which rate of reaction becomes double with each 10 degrees Celsius rise in temperature. Okay. Then like we
Then rate
defined,
of reaction becomes double.
yeah, rate of reaction becomes double with each 10 degrees Celsius rise in temperature. So we defined two factors. First was the n. N is an index value and it is like 0. It is 0 for what range? It is 0 for the range 100 degrees Celsius to 110 degrees Celsius. And for each 10 degrees Celsius rise in temperature, the value of n changes by 1. Okay, n is equal to 1 for 110 to 120. So firstly we defined n and then we defined r. R is the rate of maturation that depends on the temperature factor gamma. Okay, this gamma. So finally now we are about to define the time temperature index. That is, we are about to quantify the maturation. So moving on, write down if any organic matter spends delta T time in the temperature interval I, okay, then the increase in its maturity, then the increase in its maturity can be given as del T del Ti into r to the power n. Okay, and in this equation, r can be taken as 2 according to the Arrhenius equation. So this value is the increase in maturity if the organic matter spends del T time in the temperature interval del I. Okay. So this amount of maturity is achieved by spending this time in this temperature interval. So the total maturity of the hydrocarbon can be given by the equation. Write down total. This is the maturity for a particular time and for a particular time and for a particular temperature range. This is the maturity for a particular time and for a particular temperature range. For the temperature range I and for the time del T. So the total maturity, like that organic matter will spend different time in different temperature interval. Na? If the organic matter spend like 2 million years in the temperature and 100 degrees Celsius and 4 million years in the temperature 150 degrees Celsius. So for this couple of time and temperature, the maturity attained will be different, and for this time and temperature couple, the maturity attained will be different. So the maturity attained by this couple of time and temperature can be calculated by this equation, and this for this also can be calculated by this equation. So the total maturity can be given as by like adding all this, like adding this one, or adding further time and temperature ranges. So write down the equation. Total maturity of a sediment can be given as the sum of maturity added at each 10 degrees Celsius interval of temperature. Okay, and this is given by the time temperature index, that is TTI. Time temperature index, and this is equal to summation of del T n in Rn from n minimum to n maximum. Okay, n is what we defined n na. So so the total maturity can be given by this equation. TTI is equal to summation of del Tn over Rn. You can define this like n max is the highest temperature interval encountered, and n minimum is the lowest temperature interval encountered. And R is generally taken as 2 because the rate of reaction doubles for each 10 degrees Celsius rise in temperature. N is in what? N is in at a difference of N is calculated for each 10 degrees Celsius rise. So that's why the rate doubles for each 10 degrees Celsius rise in temperature, and hence R can be taken as 2. Okay. So this is the TTI method in which both time and temperature has been quantified. Got it?
Sir, you
Yeah.
written that R equal to 2 to the power 4. This equation I can't clear.
R is equal to 2 to the power 4. Where?
That's not 4 actually, 7.
Yeah, this is a bracket, I think. Yeah, this is a bracket. R
Okay,
is
okay.
approximately equal to 2. R is what? R is the rate of maturation, and the rate of maturation becomes double for each 10 degrees Celsius rise in temperature. And that's why like it is written R is equal to 2. This part is done. Once you complete writing, indicate me.
Sir,
Yeah.
here one equation shows that R is equal to R to the power minus in for the temperature range of 70 to 80 degrees centigrade, and another is R to the power plus 3. So in between 80 to 130, which equation can be used? R to the power plus 2.
Okay. The
Yes,
thing
yes,
is, yeah. Okay.
that part.
So the thing is, we defined like we defined like gamma is equal to r to the power n somewhere where it is written somewhere it was defined. Okay, leave it. So the thing is, I am just taking a screenshot of this. Hope I am capable of doing that. Okay, so you are confused in this. So I have written it here
Yes, in
r is
between
equal to
temperature.
okay. I have got you. So R gamma is R to the power minus 3 for this temperature range, and gamma is R to the power plus 3 for this temperature range. So what we defined is this minus 3 and plus 3 corresponds to what? Corresponds to the value n. Okay, and n is the Lopatin's first factor that is n, and n is 0. N is 0 for what range? For the range
100 to
100 degree.
100, 120.
Yeah. So for
Okay, sir,
this
I got
range,
it. Yes.
yeah. So the formula for
And
this
that's
is
and is that that's indicate the boundary between minus 3 and plus 3?
what?
The boundary of n is indicating minus 3 to plus 3. Is it correct?
No, no. This is not about like this. These two equations are an example. What will be the value of n for what temperature ranges? So the value of n is 0 for this temperature range. Okay. So the value will be what for 70 degrees Celsius to 80 degrees Celsius. For getting 70, we will have to minus 30 here, and we will have to do minus 30 here. So we will get 70 and 80 here. Since we have done a minus 30, so n is what? N is taken. So n is taken in the interval of 10 na. So we have decreased the temperature by minus 30. So n will be minus 3. And that's why we have written r to the power minus 3 for this temperature range.
Okay,
Similarly,
okay. I got.
okay, so similarly, like if you add 30 degrees Celsius in this, so the temperature will become 130 to 140 degrees Celsius. Okay, so since we have added plus 3, n will be 3. So the formula is gamma is equal to r to the power n. Okay, n will be 0 for 100 to 110, n will be 1 for 110 to 120, n will be 2 for 120 to 130 degrees Celsius, n will be 3 for 130 degrees Celsius to 140 degrees Celsius. Similarly, n will be minus 1 for if the temperature goes below this, like 90 degrees Celsius to 100 degrees Celsius, and will be minus 2 for the temperature being minus 8, sorry, minus not 80 degrees Celsius to 90 degrees Celsius. Done. So like similar to Witernite method, like in Witernite method we had certain limitations that the Witernite macerals can be reworked, okay, and it also depends on the type of macerals and all. So similar to that, it this method also has some limitations. So write down limitations of Lopatin's method. And the first is this method is simple, okay, simple summation. It involves simple summation and all, simple and versatile, but semi-empirical because like it is using ranges. It is not using absolute values. Like n is for a particular range of temperature, n is not for a definite amount of temperature, and hence this formula for time temperature index is semi-empirical. And the second limitation is valid only for areas with simple burial time and depth relationship. Then, and the third is determination of geothermal gradient is more difficult. Okay, so the second limitations comes from the fact that in general we see that like uh, if the burial time is more, then the depth will be more. But like this scenario does not act everywhere. Okay. Similarly, like for using the time temperature index method, we need to we need to like uh, classify all the temperature ranges in a interval of 10 degrees Celsius, and that is a difficult thing, okay, thing to calculate, and hence like we will have to calculate the geothermal gradient for that, okay, like so that we can determine like in what temperature ranges like it remained for what amount of time, okay, like how we will calculate like if this is the surface of the earth, if this is the surface of the earth, and we need to calculate the maturation for this particular amount of material, okay, for this particular amount of material. So how can we know the time? We can know the time of this amount of material by their depth, okay, by their depth. So that's why the second limitations comes into account. Like the time and depth relationship is always not simple. What we know in general is time increases with depth. Huh? That's what we know, na? If the sediment at the surface is of zero age, and the sediment below it will be like 10 years, then the sediment below will be of 20 years, then the sediment below will be 30 years. So what we have the common idea is that with increase in depth, the time increases. But this is always not true. This scenario is always not true because tectonic disturbances might act, and this simple depth and time relationship will not act. Okay, so that's why the second limitations comes into account. Okay, so for example, if you need to calculate the time, TTI for this thick material, we need to calculate the time interval, na? Time interval, and we can calculate the time interval by determining the depth and then relating it to time. We can we can calculate time only by relating the depth to the time. Firstly, we will calculate that depth to the first point, that is z1, and then we will calculate the depth to the second point, that is z2. We will determine the time corresponding to the z1, that is time 1, and then we will calculate the time corresponding to the depth Z2, that is time 2, and that's how we get the time, and we calculate the TTI. But like the time and depth relation is always not directly or very simple. Sometimes it can be very like complex due to tectonic disturbances and all, and hence these are the limitations of this method. Okay, so there are some correlation between different types of methods we discussed. So write down correlation between TTI, that is time temperature index, Wittenite reflectance, that is R naught, and thermal alteration index, that is TI. We discussed that thermal index is a 5-point index. Okay, 5-point index. So for different stages, we have different values of TTI and all. So first write down onset of oil generation. So onset of oil generation takes place at a TTI of 15 and R naught of 0.60. We already discussed about R naught. For TAI, it is 2.6. And for LOM, okay, we will discuss this LOM later. What is LOM? Write down this, draw this chart. LOM is level of organic metamorphism. Second point, peak of oil generation. So for TTI, it is 75. For R naught, it is 0. About 0.9. For TI, it is about 2.9. And for LOM, it is about 10.5.
Is it 15 TTI?
Yeah, 15. For the first, it is 15. End of oil generation. TTI 160, 1.35 R naught, 3.3 TI, and 11.5 LOM. That is level of organic metamorphism. Fourth is upper limit for occurrence of oil with API less than 40 degree. So API is less than 40 degrees Celsius. So you guys tell me, like, it is for light oil or it is for heavy oil?
Heavy oil.
Heavy oil. Hello? Heavy or light? Hello? Somebody? So the API is inversely yeah, say. Somebody is trying to say.
Greater than 40 means the light oil. But
API is inversely proportional to density, na?
yes,
So if API is large, then density will be low, and if API is low, then density will be high. So you guys need to revise. You guys move to your previous pages, previous notes, and see, like, and confirm whether it is for light oil or heavy oil. Right on for fourth, it is 500, then 1.75. There are two ranges. One is for 40 degrees Celsius and one is for 10 degrees Celsius. You guys please try to see that in your copies. then 3.6 for this, and then 12.5 for this. And write down the fifth upper limit for occurrence of oil with API less than 50 degrees Celsius, and it is 1000, 2.0, 3.6, and 13.5. First column is for TTA, then second is for R0, the third is for TA, and fourth is for LOM. Sixth is upper limit for occurrence of wet gas. It is 1500 for TTI, then 2.2 for R0, and then 3.75 for TA, and 14.5 for LOM. Seventh upper limit, that is UL, for occurrence of dry gas. Dry gas occurs after wet gas. So you can see the phase change here also. Firstly, we get oil, then we get uh, firstly we get heavy oil, then we get light oil, then we get wet gas, then we get dry gas, and it is like large 65,000, then 4.8, greater than 4.0, and 20. Upper limit. So like liquid sulfur. This one is not important. Write down till seventh only. There are a few more correlations, and we will discuss it in the next classes. Any confusion in the TTI or Rockable or anything we studied?
Excuse me, sir.
Yeah, hi.
There's few question in the chat box. Can you answer those?
Okay, I'm trying to see the chat box. Why the rate of maturation doubles for each 10 degrees Celsius rise in temperature? और क्या क्या questions आए हैं? The first one is why EA is required less in later stages than initial stages, and the second is why temperature is an important factor for oil formation. Okay, so I will answer the first one first. I'm trying to take a screenshot of this. Okay, like the first question is why EA is required less in later stages. My screen is visible?
Yes, sir.
Yeah. So we discussed that like to start the reaction we need a large amount of energy. And this is like you can say this is a rule. To start any reaction we need a lot of energy. You can take the example of any reaction. To start the reaction we'll need a large amount of energy. For example, yeah, for example, N2 plus 3s2. 3s2 gives 2ns3. Okay, so this is the reaction for the formation of ammonia. So like we know that nitrogen is in the atmosphere. Okay,
nitrogen is in the atmosphere. Hydrogen is also in the atmosphere, but they are not reacting in the atmosphere to form ammonia. Na? In the atmosphere, we have 25 degrees Celsius of temperature. Okay, but this amount of temperature is not sufficient for the formation of ammonia. Okay, in the atmosphere, these two things are not reacting, and we need to provide a greater amount of energy for them to start reacting. Okay, but for them to continue reacting, we need a lesser amount of energy, because once they start to combine, the molecule find a path. The molecule find a pathway to go and pathway to how to combine. Okay, so like for every for each temperature range, molecule behaves differently. Okay, तो अगर हम टेम्परेचर 100 डिग्री सेल्सियस रखेंगे तो मॉलिक्यूल अलग तरीके से बिहेव करेगा और रिएक्शन का रिजल्ट क्या होगा, कुछ अलग होगा. अगर टेम्परेचर 200 रखेंगे तो रिएक्शन का रिजल्ट कुछ और होगा. तो अगर हम टेम्परेचर 100 रखते हैं तो मॉलिक्यूल्स को एक पाथवे मिल जाएगा कि हमको किस तरीके से रिएक्ट करना है. ठीक है, और फिर वो उसी तरीके से रिएक्ट करते रहेंगे अगर हम टेम्परेचर को मेंटेन रखें. तो तुम इससे भी ये चीज समझ सकते हो कि अगर जैसे घर में तुम रोटी पका रहे हो, if this is a pan, okay, so to for the pan to reach 100 degrees Celsius of temperature, we need a lot of heating. Okay, we need to heat this pan for what, for like for say 15 minute or 10 minute, we need to heat about this time, like 10 minutes we need to heat for 10 minutes to for the pan to reach 100 degrees Celsius. But for the pan for but for to keep the pan at 100 degree Celsius, we need to provide a lesser heat ना. अगर थोड़ा थोड़ा भी हीट देते रहेंगे तो तब भी पैन क्या रहेगा, फिर तब भी पैन उतना ही गर्म रहेगा. So this is the scenario, like to for the pan to reach 100 degrees Celsius, a lot of amount of energy is required. But to maintain 100 degrees Celsius, a lesser amount of energy is required. Okay, so this is the fact why we need lesser amount of energy to continue the reaction and more amount of energy to initiate the reaction. And the second question was why temperature is an important factor for oil formation. So for this thing maturation, firstly we have organic matter, then we have kerosene, and then we have oil. So for the conversion of organic matter to kerosene, a lot of processes is involved. First is diagenesis. Okay, diagenesis, and for the formation of kerosene to oil, the process involved is catagenesis. In catagenesis, time and temperature are involved. Time and temperature. So these two things are essential, and why they are essential? So you must know the concept of cooking. Okay, so cooking means making anything mature, and cooking requires both time and temperature, and you can know this by the concept of pan. Like if you are cooking anything in pan, you need both temperature and time. Okay, and that's why both temperature and time is needed. Like you are cooking now, you converting the organic matter to to kerosene and then to oil. Okay, like you must be aware of the fact that when you heat out chicken, you must have cooked chicken or you must have seen chicken cooking. Like if you cook chicken in a pan, then if you continue heating, then the what happens is the chicken releases some oil. Or like you can also correlate it from the fact that if you heat some animal fat, this is a very good example. Okay, if you heat animal fat, okay, like animal fat, then the animal fat does what, the animal fat melts, the animal fat melts and produces oil. And this is the concept of oil formation in the petroleum geology. Animal fat is what, animal fat is lipid, and lipid is being converted into oil, and this is the pathway for oil formation, and it requires time. Okay, the animal fat is what, animal fat is an organic matter. If you bury it, if you provide it temperature, it will generate oil. And the same scenario, this happens in the kitchen as well. Like if you heat the animal meat, it will generate oil. So that's why temperature is needed. It is a cooking process. And the third question is like, why the rate of maturation is double for every 10 degrees Celsius rise in temperature? So the thing is, we discussed RNA's equation. RNA's equation says that K is equal to A into e to the power EA by RT. So K is what? K is rate constant. Rate constant, that is the rate at which the reaction is taking place. A is Arrhenius constant. A is Arrhenius constant. Okay, and E is the activation energy. R is universal gas constant. T is the temperature. So if you calculate K, if you calculate K for T1 and then calculate K2, that is K2 for E to the power R T2. Okay, T2, and T2 is what? T2 is 10 degrees Celsius more than T1. T2 is T1 plus 10 degrees Celsius. So what will happen is if you calculate this two equation, like put A is equal to 1. Okay, take anything. Take A is equal to 1, EA is equal to 1, R is equal to 8.314, and T1 is equal to, take anything. Take 100 degrees Celsius or take 100 degree Fahrenheit, and then take T2 as, if you are taking T1 as 100 degree Fahrenheit or say 100 degree Kelvin, then take T2 as 110 degree Kelvin. Okay, and take E1 as 1, take A as 1, and calculate K1 and K2. You will get some value of K1, you will get some value of K2, and you will ultimately find that K2 is approximately double of K1. So this fact that the rate increases, the rate becomes double for each 10 degrees Celsius rise in temperatures comes from this calculation. If you put temperature more than 10 degrees Celsius, the rate will double. You can calculate this, like take T1 is equal to 100 degree Kelvin, T2 is equal to 110 degree Kelvin, EA is equal to 400 joule. Okay, and what else is needed? A is equal to 20, and then calculate K1 and K2. You guys do this as an homework. Okay, calculate K1 and K2 and do let me know in the next class what are the values of K1 and K2, and most probably K2 will be K2 will be double of K1. Okay, got it?
Yes, sir.
Hello. Okay. Okay, thank you guys. Good night.
Sir?
Good night, guys. Bye.